Thanks, everybody. So before I start, this is my first talk back since COVID, so I'm a little rusty, so please bear with me. Also, I've been getting into meta-modernism lately. Everything Everywhere All at Once is my favorite movie. I decided to get a little weird with this talk, so please just give me a little, I'll get there. You'll get it. OK. Hi, everybody. I'm Steve. This talk is called I Learned Embedded Rust, and so can you. And that's basically just the premise of the talk. I'll just say, like, straight up, it's basically my position that you should is a complicated word, but if you're interested, I believe that you can do lower level programming than you currently do, and you should try if you want. So some background on me. I just mentioned a couple different things, but there's also some like, I hate talking about myself, but there's like extended background lore here that's like relevant, so we'll get into it. So I'm one of those people that started programming when I was a kid. I have very complicated feelings about that because of reasons that I won't get into. But I started off learning GW Basic, and then C, and then eventually C++, and then Java and Perl. And so that was the kind of stuff that I did from when I was like 7 till I was in like high school. And then once I got to like college and I pursued a computer science degree, I was actually really interested in compilers and operating systems design. So I scheduled my like class schedule to get into that as like close as possible. So I really, really wanted to do that stuff. And so I wrote a lot more Java and some C and some Ruby and some PHP. But like when I looked at the job market in 2009, it is like operating systems developers and compiler developers. Like there's not very many jobs for doing that. However, this thing called like Web 2.0 was happening, and the web was a very exciting place to be. And so I got an internship at a company that did like podcast hosting and did PHP stuff. So I started my professional career in PHP. And then I read some stuff about unit testing and Rails, and I went, oh my god, our PHP code base is so buggy because we don't even really have good tests, and I could do this TDD thing and it'd be awesome. And they all kind of went, yeah, cool, like you're the intern. We're not going to rewrite our entire application in Rails just because testing is cool. But I like kind of wanted to do that. So I got really heavily involved in the Ruby and Rails communities over the next couple of years. And before I actually worked on Rust, I was working on Rails. So I had commit bit access to Rails, and I was doing all that kind of stuff. And that's kind of when I started doing this conference speaking thing and like open source and stuff. So a lot of people kind of know me as like the Ruby guy who started doing Rust. But I kind of had this background of things different than that before. But so I've spent the last 10 years. I'm one of the few people that can legitimately say I have 10 years experience in Rust. I started using it in December of 2012. So we're just past that now, and so it's really been cool and weird because like to me in some ways Rust still feels like 40 people in an IRC room, not like every large tech company using it for serious things. And I meet random people who are using Rust stuff now, and it's very cool, but also a little bit strange. This is relevant to this talk specifically because, as I said, a lot of people knew me from the Ruby world, and several other early Rust folks were from Ruby and Python and JavaScript places. And so they would like get online and post things like, oh my god, there's these Ruby people that think they can do low-level programming. Rust is obviously a toy because they clearly don't know what they're talking about. And that attitude sucks. And it sucks because, first of all, like just because you like scripting languages doesn't mean you can't understand things that are not that. So that's like kind of weird. But also, like I was extra mad about it because I was like, man, I only got into Ruby because I couldn't make it in compilers because of the job market. Like I actually like did like me and my friends were writing an OS together in college. I'll get back to that at some point. But and so like I'm not just like some web person, although I also think that people discount the complexity of the web. But I'm getting far ahead of myself. But the point is that I think this attitude is very pervasive in the development community, and I think it sucks, and I would like to convince you that it is wrong and that you should not listen to it anymore and not like perpetuate these beliefs about low-level programming stuff. Nowadays, I work at Oxide Computer Company, as mentioned before. Brian gave a talk the first day, if you were here for that. The short of it is we build servers and we sell them. That's not super relevant other than the fact that it's called Oxide because literally all the software except for the front end of the website is written in Rust from like the firmware the whole way up through the stack. And so when I went to go work there, I had a lot of self-doubt because even though I knew this stuff and I had been doing these kind of things before, this kind of pervasive attitude really got to me. And I was like, do I have the ability to like work it? Like the team I wanted to work at in Oxide was the embedded team doing low-level firmware stuff. Like that was what I actually wanted to do. But I had this like real crisis of confidence about can I even do that? And Brian's not here, so he can't tell me my memory of this conversation is wrong. Maybe he'll watch the video and tell me if I remember this right or not. But when I confided in him that I was like, I don't know if I can do this or not, and like I want to be able to perform professionally, he told me a story about how when he got out of school and he went to go work at Sun, the like first week they're like, go fix this kernel bug. And he was like, what do you mean? I literally just like I just got my degree. Like, what's the deal? And what his boss then told him is like, kernel programming is data structures and algorithms. You know data structures and algorithms. Like, a kernel is just a program. It's not special. And you only have this weird mental block because you think about it as something special. Now, they might be unfamiliar data structures and algorithms, but you've learned unfamiliar data structures and algorithms before. So like, I believe in you. And then Brian went on to do all the things that Brian did, and he passed that knowledge down to me. And so now I'm trying to like pass that on to you all because I like truly believe this is the case. And so we're going to sort of talk about these unfamiliar data structures and algorithms and how like you probably can learn them a lot faster than you think you can, and lots of other stuff like that. So, but first, before we get into those things, I want to talk about why Rust specifically. Obviously, given that I wrote a book called The Rust Programming Language, I have some bias. But I do think that Rust is uniquely suited to make for a good environment for people learning embedded software development. And that's because of a couple different reasons. The first one, I'm not going to give a ton of background on Rust because, ironically, even though it's a 50-minute talk, I'm not sure I have time. But basically, if you don't know a whole ton about Rust, here are some properties of the language that I think make it good for this task. So the first one is it has what I've described as an intense type system. This is because strong means certain things to type people, and I don't want to argue about that. So what I mean is, when you write programs, you get a lot of type errors. And the reason that that's cool is that type errors happen at compile time, not at runtime. And in the context of embedded, that means they happen on your nice desktop computer, not on the microcontroller. Because when stuff goes wrong on microcontrollers, as we'll talk about later, even being able to figure out what goes wrong is like hard. So if it's a nice error message that happens up front, then that's just a much better experience and a much better like learning situation for a lot of people. And related to that, part of the reason why that's good is also because the Rust team is very dedicated to the idea that compiler error messages are important and something they invest time into. So there's just like a general policy of the Rust project that if an error message is confusing, file a bug, and we need to make it better. Ironically, Rust's error messages at this point are generally so good that I blindly trust them. And so the 1% of the time when they're bad, it can lead you down the bad path because you're so, like, if you haven't programmed in Rust before, a lot of times the compiler will say, hey, here's a problem, but then it also will literally suggest to you the fix that will make it work. And so you kind of get into this habit of it's like, oh, by the way, I see what you did there, and also, like, it might be this. And it turns out it's right often enough that that's a really helpful like way to learn. So I think that's very good. The third bullet point, library design. We're going to talk about using some libraries a little later in this talk. But the libraries that the Rust folks who are working on embedded systems have built are designed to work with those previous 2 points of mine. So they make strong use of the type system to guarantee that certain things will happen when they're supposed to happen and all that kind of stuff. And that's like more of a cultural value than it is like a prospect, like a particular part of the language itself. But it is a very real factor. And so I think that's been really good, and it's a good reason to use it. There's also some more complexity there we'll get into. But yeah, I don't want to keep jumping ahead of myself. And then the last one is like sort of nice tools overall. So a lot of the tooling in the embedded world, like vendors expect you to use their tooling with their chips, and it almost universally sucks hard. Like, oh, our IDE is free, but you gotta like give us your email and sign up for the marketing list and like download an installer and like do all these things, and then it turns out it's like a version of Eclipse from 6 years ago that they bolted some features on, and it's just like not good. Whereas with Rust, a lot of the people who have built tooling around this stuff have done it from the perspective of like, what if I considered that humans would maybe want to use this tool and are not like forced to because we made them do it? And so just the workflows fit into all the normal stuff you do. So like I use Visual Studio Code, and a lot of my coworkers use Vim, and that's totally fine because we're not like actually beholden to vendor tooling in a way. And so I think that that is like significantly nicer than other ways of approaching this. Okay, so that's Rust. So next I'm going to go into an extremely obvious next topic, which is a detour into fashion. So who's seen The Devil Wears Prada? Cool. It's my favorite movie. There are minor plot spoilers. They don't matter. It's since 2006 when this movie came out. I feel like I can't not spoil certain things any longer. But this is like kind of sort of a semi-joke, but it's also very real. Alan Kay has this quote. Everybody's been quoting Alan Kay all this conference, so I will quote Alan Kay as well. And he says, software is a fashion industry. And I think that that is actually like a very deep and meaningful thing, even though I'm not sure that's the way he intended it, but I think it's actually like very true on like a lower level. And this is why I was trying to match the purple of the slides to my shirt, because I feel like if I'm out here to talk about fashion, I should like be a little better about that. So the way I explain fashion to programmers, because I am also learning. This is kind of like I'm taking my own advice about embedded development, but applying it to fashion lately. So I've been trying to like learn more about what it means to like dress like an adult than not. And so I would describe fashion as being like the API of being perceived. Like when you talk to another person, there's all this stuff here that you look at and you have some sort of like visceral immediate reaction to, or if you don't, like the other way is also true. You are talking to somebody and it's very likely that they are informed by what you're saying by the way that you present yourself. And so I'm taking this in a very broad sense. Because for example, like memes are sort of fashion. Like if I show you this guy, there's no text. He's like not talking to you, but you like, there's vibes, basically, is what I'm saying. And those vibes can change. Like if I show you this one, it's got very different vibes. And it also harkens back to a certain period of the internet and all those kind of things. And like if we go even further back, right, we get like this stuff. And like, you know, this like aspect of the way that we present ourselves to the world is like really, really important. And that's like ultimately what fashion is really about in many senses anyway, or at least to me, that's like what it's about. And it's also really important that fashion is sort of like a language that's constantly in conversation with itself and its present and its past as well as its future. So, for example, does anyone know who this is? This is FDR as a kid. And that's because back then in the late 1800s, we didn't have things like Velcro to make it really easy to like take pants on and off. And children are like food to poop compilers, right? So it just like was easier, and this is again my understanding, I might be wrong about this, I'm still learning these things. It's my understanding that dresses were not considered a gendered thing for small children in the 1800s for these like practical reasons. And in fact, it wasn't until you like came of a certain age where you had dexterous hands enough to either like button up your pants or like shove into a dangerous machine that you like graduated to like wearing pants because you could like handle that yourself because you were now old enough to be an independent adult. And that there was like I think it was breeching or britching was the like this like sort of coming of age ceremony almost where you like stopped wearing your children's clothes. And it wasn't even about gender then either. It was more just like those are children's attire and now you're an adult so you should be wearing adult clothes. And so you could tell by looking at somebody if they were too young or not because of the way that the fashion was perceived. And so we don't do that with children anymore because the conditions have changed and so we do different things now. But like the point is like this stuff has context and it's rooted in the world and the way that we interact with the people and it changes over time and it's like a language we use to communicate. And what this also implies is that it's not possible to like opt out of fashion unless you don't exist anymore. Like this isn't like saying anything or doing anything because there's no interface, there's no back and forth. And as soon as you have like a mechanism or a channel of information, then you're able to like do this kind of stuff. So anyway, Devil Wears Prada. These are the two main characters in this movie. You got Miranda on the left, played by Meryl Streep, who is like amazing. And then you have Andy, short for Andrea. She uses the boy's nickname because she's like one of the cool boys, not like one of those girls that cares about fashion. And the sort of conflict about Andy sort of going from a like I don't care about any of this topic to like understanding this is a real thing that you can interact with is sort of the like focal point of the movie. And this very famous scene that I kind of wanted to like read, but I could never do Meryl Streep justice, and so that's like not like a thing. But there's this really famous monologue in the middle of the movie where this assistant goes, hey, we need to pick what belt goes with this outfit. These two things are so different. And she like kind of chuckles. And she is the stand-in for the audience basically at this point, because like, I don't know about you, but I look at those belts and they pretty much look the same to me personally. And so there's this extended monologue about like, oh, so you think that this is not something that you interact with at all. But what you don't know is that the color blue that you're wearing was actually like referenced in like 20 years ago in this one particular fashion show, and then that made other people pick up this color of cerulean specifically, and so like it filtered down eventually to the point where it was in regular clothes that you wear. But like you think that you're not interacting with fashion, but you are. You just are. It's just subconscious for you. You like choose to ignore it, but that doesn't mean it ignores you. It is impossible to like get away from. And so this is like the one particular quote here at the end. It's sort of comical how you think you've made a choice that exempts you from the fashion industry, when in fact you're wearing a sweater that was selected for you by people in this room. And so I've been going on this journey with clothes and learning about stuff lately. And so I would say like fashion isn't impossible to understand. You just haven't tried to like actually understand it yet. And so I think this applies to embedded software development. So my hope is that this is you now, and then this is you soon. I think it's really important in this metaphor to acknowledge that like this doesn't mean she's dressed poorly in this image, right? It's just like an unconscious thing that you just kind of do. And then this is more of a conscious, deliberate choice to say something about yourself to the rest of the world. I think that subtlety is sometimes kind of maybe like left about people. The last thing before I get out of this extended fashion metaphor is I think that you do actually understand more about fashion than you would consciously think. Like this guy, right? Like, I was obsessed with Steve Jobs, and I have complicated feelings about that now, but I was like 13 when I was first introduced to this guy, so whatever. My brain wasn't fully developed yet or whatever. The point is that Steve Jobs had this like fashion uniform, and he was actually really into the concept of a uniform. He actually wanted to make everyone at Apple dress this way, and they were like, no. And so he said, fine, I'm going to do it. But this is like deliberately chosen with a particular ideology in mind, and he like talked about it publicly. So he was like, I want to focus on meaningful, creative decisions in my work. I don't want to have to think about how I dress myself, so I've decided that this is my uniform, and it's going to remove this kind of like choice that I find distracting so that I can focus on what's important. And so the minimalism and like the whole like the vibes, like he had a deliberate particular choice, and like you probably know that Steve Jobs always wore a black polo and jeans, or like at least this is not an unfamiliar image to you. Even if you didn't know that there was like deliberate decisions behind there, like the minimalism kind of like implies that. We have other fashions in technology. This guy, representing the Patagonia section of the like VC Tech Bro area, like this became such a fashion meme that Patagonia refused to sell tech company branded Patagonia vests a couple years back because they were sick of the association because they thought it was ruining their brand. And like we all recognize this guy, I'm assuming, if you've been in this industry, and that's totally fine. I'm not saying this guy is bad, but I'm just saying like you may have not thought you had an opinion on clothes before, but if you look at these two guys, you probably do have some subconscious opinions about who they are and what they do and whatever. And then you got people that dress like this. This is me wearing another form of tech outfit, kind of like wear, the GitHub hoodie, the backpack, and that kind of stuff, all in black. You can see I've really learned a lot. I've graduated. I'm now wearing colored shirts instead of all black all the time. So we're all evolving. But just like, yeah. So anyway, this is like during a time where I would have said that I didn't participate in fashion, but like I definitely was. I just like didn't know it. And so, yeah. Okay. So let's go back to the main point of stuff. I'm gonna stop talking about clothes now because it's already been a little while. So you can do this. Don't let others, think or imply that you can't, because I believe that you can. When I was choosing to do this web development stuff, one of my friends in college told me, I don't want to do web development. It's too hard. I prefer assembly language. Which is a sense that many of us would be like, what do you mean? And he's like, if I write add register 1 to register 2, it's going to do exactly that and nothing more. But in web development, you write a script in a programming language, and then you bundle up in a markup language, and then you ship it to the other side of the world on a totally different computer that you don't know at all, and you somehow expect that house of cards to work. Like, that's too complicated. I want like add 1 to 2. Like, And so it's like much more straightforward. And so I think this framing and this attitude has like informed me ever since. But I also think that, like, as I mentioned before, there's sort of this common meme that like low-level programming is hard and web programming is easy. I don't really just want to convince you that lower-level programming is easier than you may think. I also would like you to maybe acknowledge that if you're a web developer, it's actually more complicated than many people give you credit for, and you are doing deep, hard technical work that like some jerks don't want to recognize, but I think that you are. So now that I'm done with a bunch of that stuff, let's talk about Hello World, which is important. So the way I'm going to structure sort of like the more in-depth technical part of this talk is I'm going to give you an overview, and that's because this is taken from a tutorial that I'm going to link at the end. I don't want to read a tutorial to you, so I'm not going to go over every step, and I'm going to combine a couple of different resources. But just like this is a high-level kind of like, I want to talk about it in a sort of abstract way, so there's going to be some pieces missing, and I'm going to have places for you to go to fill out the rest of it. But for this purpose, we're going to be talking about this BBC micro bit. And so this is very common, and this is actually how I would like recommend that you start to learn this kind of stuff. There's several tutorials that I've got at the end, and they all point you to a piece of hardware that you can actually buy that they've run the tutorial on before, so that you're not fighting with, like, do I know if this stuff even works on this thing? And so this is how I got started, not with this particular one, but with the separate, a different tutorial. But just like the point is that to get started with this stuff, I would suggest that you like find a tutorial and then buy whatever piece of hardware it is that it says that it needs, and then go do that to start. So I think the BBC microbit is like $20 or $30. So it's not super cheap, but it's not super, super expensive. And basically what you do is the top there is like a USB port, and you plug that into your computer, and then we're going to write some code, and we're going to send it to it, and it's going to work. And the code we're going to talk about today, it kind of has some buttons and some other fancy stuff on it. But all these things, this is a 5x5 array of LEDs. And the default hello world in embedded land is not to print hello world, because this thing doesn't have a screen, so that kind of is sort of nonsense. But it's blinking an LED. And that's how you know I've got my development environment set up. I can push code onto the thing and like make it like actually work. So we're gonna look at several versions of what hello world looks like at different levels of abstraction. So this is what I would call the like highest level of abstraction version of this code. And we're going to go into it not super, super intensely, but just kind of lightly. So if you haven't seen a ton of Rust code before, this is kind of what Rust looks like. There's sort of a lot of extra annotations that are not always in everything. But the most important part at the top for embedded programming, we're going to opt out of a main function being made for us, and we're going to opt out of the standard library. Rust has a split between sort of a standard library that doesn't rely on having an OS at all, and then a second layer of the standard library that does all that OS stuff. And so what this directive does is basically say, throw out all that stuff about threads and file systems and things like that, and we just want to keep the math and the algorithms and like do that kind of stuff. And then we're going to use some libraries, and I'm not really going to go into them right now because it's not really what's super important, but this is just like bringing stuff from various libraries into scope. So this particular board uses a processor called the Cortex-M. So there's a Cortex-M runtime library that we're using. And then the microbit folks have also published what they would call like a board support package that's like, here are higher level functions that are specific to this particular piece of hardware. And so to start, we're going to use that. And so then in our main function, one fun thing about embedded main functions, and if you haven't done Rust before, you may not have seen this, or even if you've done Rust before, you may not have seen this. This little function main returns never. This is saying like this function is never going to return. And that's actually really important, because when you're running on an embedded device, like it's not like, OK, the program's over and we exit and then nothing happens. Like that just means the whole thing turns off. And you probably don't want it to turn off after it blinks one LED once. So this actually just turns it on. It doesn't even blink. But the point is that we call this board.take. .unwrap is for error handling. We're basically just saying like if anything goes wrong, blow up and don't do anything. So that's why that's repeated there. But we're going to like sort of grab a reference to the board, and then we'll say, OK, call the display pins, and then column 1, I want to set that one to low, and then board display pins, row 1, set that one to high. And so that would like turn this one off and turn that one on, or do that stuff, and then just like loop forever so that we never return. So this is kind of using these high-level APIs to do this kind of stuff. And this is what I was referencing earlier with the design of the libraries, is that, you know, this is like not super, super like low level even really. And it's designed in such a way that like you can't, well, we don't even have the understanding to understand why this is a nice interface yet. We're going to go into we'll go into the lower level version, and then you're going to see why this is so nice and why the compiler helps you. But imagine autocomplete, right? We have all these names and stuff. So if you have an IDE, this will autocomplete, and you can be like, okay, cool, like display pins, which ones do I have? And it'll display all those rows and columns. Like that's like sort of the tooling helping you guide you through this process. So how do I actually use this thing? Well, we talked a little bit about tools. And there is a bunch of different ones, but one that I really like is called cargo embed. And you basically just say cargo embed, and it goes, cool. It's going to build your actual program, and then it's going to double check if a thing is actually plugged in. And if it is plugged in, it's going to upload the contents onto the particular little microprocessor, and then do a bunch of debugging stuff. But like reset the target means start it up. There's no like the way embedded folks talk about things. It's never turning on. It's always in a state of like returning back on. Like we're resetting from the start. There's no like on or off. You basically are always like resetting. But anyway, and then it starts up some debugging stuff. We'll get into debugging in a minute. But just the point is like to send the code over, this is all you have to type. And then in theory, if you've done everything correctly, your LEDs will start changing on your device. So this is very straightforward, like kind of hello world. So let's talk about what it would look like if we weren't using that board support package. And this is going to be closer to what you may think of as traditional sort of like low-level programming stuff. Mostly, this guy named Alan Perlis, who has a bunch of very witty sayings about programming. And his one about systems programming is when you have to start caring about the irrelevant details. So if we weren't going to be using our nice library, our code, there's a second page to this. This is not all the code. This is basically the same general idea, but we're no longer using that board support package, so we have to do it all ourselves. And so here, GPIO is this general purpose I/O concept. So when we're talking to hardware, we often use various things like this that then you have to configure properly. And so we set it to this particular hexadecimal address, and then we have all these like offsets and all these fields. This is a bunch of junk that you basically look up in a giant 200-page PDF. We'll talk more about giant 200-page PDFs later. But like there's some sort of documentation you would follow that says, put these numbers here, and you kind of just do it, and you hope it works. And then in the main function, we're going to like configure the individual pins as push-pull outputs, which is words I have not explained. Those are a thing. I'm not going to explain what that means in this talk because I don't have time. But just like we have to configure the actual like hardware itself. And then we call this like write volatile by saying like, OK, I want it to be an output and disconnect the input and disable the pull and do this stuff. And so we're kind of like, this is like setting a variable. But because hardware is weird, we have to do it more complicated with this volatile instruction instead of just saying equals, because compilers are really good at eliminating your code. And if you assign something to a variable and you never read it later, the compiler goes, ah, you assigned something to a variable and you never read it. So I'm just never going to bother to assign the variable in the first place because that's more efficient. But when we're like, but what's reading it is the hardware. So like the language can't know that that's what you're doing. So you'll often see this write volatile and read volatile. And the idea of a volatile variable is it's saying, hey, compiler, I know that you don't know if this variable is being used, but I promise you it is. So please don't like move it away or whatever. So we use all those numbers we configured earlier, and we write those to those two things, and then set this pin load to high, and then turn the LED on, and then write out those things to this, and then loop. So if you want to get a little more low level, you could also write this hello world this way, using this API. And there's some, this is actually nice. If you haven't done embedded programming in like C or C++ before, this feels much more similar to the way of doing it, but there's a lot more type safety, even in this code, than there would be in those things. But it's like much more complicated. The nice part though is you get to learn like more about how the details work, which is like kind of cool. But it is a lot more code, and so you sort of like graduate between these higher level and lower levels areas. Like even within embedded programming, there's high and low level stuff. Like we think about it as this unified low level way, but I've just shown you sort of like two equivalent bits of code. They'll compile to literally the exact same thing, modulus and maybe small differences. I haven't actually checked that yet, but they should. And but one is like a little easier to use, and the other one is a little more low level. So yeah. Anyway, now that you've started to like learn a little bit about these things, you're like on your way towards having better fashion. So that's kind of the general thing. We're going to talk real briefly about some important concepts you need to know. I've referenced one or two things, but there's some things I think are particularly useful at the start of your journey that I kind of want to explain like a little teeny bit. And some of that is sort of like I've kind of already implicitly sort of talked about this, but One really cool thing about learning, a thing I love about our field is that if you start working in a different area of it, you have all this new terminology to learn and all these new APIs and all these new things to learn. So I'm going to point you towards some vocabulary words that may be useful to you at the start of your journey. I think the most important one is cross-compiling, and this is something that's actually gotten much, much more into the mainstream ever since Apple started using ARM processors instead of x86 processors. So the idea of a cross-compiling is instead of taking the code and building it for my machine, I'm going to build it for a machine that's a totally different kind of processor, right? Like my little board that I've plugged into my computer, this is an x86 computer, and that's an ARM chip, so they just literally don't work the same as the processor, as on the processor level. So we need to expressly tell the computer, hey, compile for this particular architecture, not for the one you're running on. And so that's a really big thing. This is another example where tooling is much better in Rust than in other places. Actually, that's not always entirely true, but it's also like Clang. So let's not even get Rust in the equation. Let's just talk about Clang versus GCC really quick, which are two C and C++ compilers. GCC makes you build your own copy of the compiler specifically to cross-compile. So it only knows one input and one output. So if you want to start going from x86 to ARM, you have to build your own GCC or download a pre-built package of it. But the point is it's a separate compiler. The way that Clang and also Rust work is that every compiler is also a cross-compiler. So you just pass it a flag saying, please compile for this other architecture, and it does it. So that tooling is way nicer, straight up. Second one is flash memory and flashing. So it's really common, you're not putting a hard drive onto your embedded system, right? So with storage, you usually have flash memory, and so therefore the act of copying your code from your host computer onto this embedded device is called flashing. So people talk about flash memory and flashing, and you only have so much of it. And it's kind of funny because the concept of embedded has grown bigger. So people will talk about embedded devices with 1 GB of RAM in them, and that's stretching it a little bit. But whatever, do whatever you want. But just sometimes you have to care about how much memory your code is actually using because these devices are small, and therefore that's a thing you have to think about. The next one is serial ports, one of the sort of older I/O interfaces that exist. So a serial port is basically just a way of passing bits back and forth between two things, and it's kind of the easiest and simplest way of doing that transfer, and so it's used in a surprisingly number of things. It also has some flaws, and we're actually going to go over a protocol that's improving on that in a minute. Semi-hosting, parentheses, no. There's this concept called semi-hosting that you can do to get sort of printf style inputs. You can say print a message to the screen, and it'll print it out on your host computer instead of on something on the device. And it sounds really cool and convenient, but the problem is the way it's implemented in the hardware is crazy and bad, and so you want to get away from it as soon as possible, even though it feels convenient. The way that it works is by shutting the processor off and then doing some work and then waiting to hear back and turning it back on again. So I had a bug where I was trying to debug this thing was talking to this thing, and there was a timing problem with their communication. So when I added the printf statement and it shut the processor down, that meant that it paused it for long enough that the timing problem disappeared. And so literally adding the print would make my code work or not work because of the timing aspect. And that's the problem with semi-hosting. So you'll hear about it, but just ideally don't use it because you'll just cause yourself more pain later. The last one is a thing called pin. So people talk about, you saw in the code earlier, it's set this GPIO pin to whatever. That's because often it's literally a physical kind of pin on the thing, but we talk about it conceptually in software, and it basically usually just means a memory location you write stuff to do a thing. Okay, so how do you actually learn beyond this talk though? Because I spent all my time on fashion and none of my time on code. There's more code coming. But the process of learning is, I think, an important skill and one that works a little bit differently. So as you sort of advance on this journey, this is the way that I think you should go about it. So pick some sort of project that interests you. There are good ideas on this website called Adafruit. I don't know why it cut off that URL like that. Gosh, category/projects of sort of pre-built ideas of maybe here's a clock with a temperature sensor on it, or you want to display some things, so here's a display and a temperature sensor and a chip, and you can put them together. And so browsing through that can give you an idea of a project that you want to do. And then you kind of got to read some documentation, and then if you find something you don't know, you read some more documentation, you write some code, you try it out. Optional, but I find mandatory usually, cry into your debugger because something will go wrong and you don't understand why, and you feel like it should all work and you don't know what's going on and everything's terrible. And then finally it works and you succeeded. Great, success. This may sound really basic to you, but my point is like this is what you do in web development. Like some of the details are different, but like fundamentally the way that you go about doing this development is not, it's still writing code. Like it's not anything that you don't already know. And when I mentioned serial ports earlier and how serial ports are kind of bad, we're going to talk about a protocol called I2C as sort of an example of this kind of low-level thing. And I remember learning about this, and my first reaction was like, that just feels really obvious and basic. Why is this hard? And the answer is there's a lot of details, actually, that I'm not going to talk about in this talk that make it awkward. But in the fictionalized basic version I'm showing you today, it's actually very, very straightforward. And the way that this works is you have one chip that's sort of like in control of things, and then you attach other peripherals or other devices to it, and they use these two different data lines to communicate. This is one other thing that I want to show you that's a thing that's a little unfortunate about embedded programming right now, is there's a lot of usage of the master-slave terminology, and people are trying to change that, but it's still true. You're going to come across in documentation. I'm going to use the word server and client because I'm talking to web developers. A lot of people will use controller and peripheral, but like people are still sort of figuring out the way that you talk about these things. But so we have like a server, which in our case is like the processor, and there's sort of two like paths of getting data out. There's the clock line and the data line. And then we may have different clients. Like this may be a temperature sensor, and that may be a display of some kind. And so if we want to take information from the temperature sensor and then put it on the display, what's going to happen is our server is going to ask this particular client of the temperature sensor, hey, what's the temperature? And then it's going to reply with the information. And then it's going to go send that information over to the display and say, display it. So this is like classic Web 2.0 stuff. You're like mixing, mashing services together, and you're like doing fun things with a lot more ones and zeros. And so like what happens on sort of like the physical level, in my understanding, I'm not an electronic engineer, but like the clock basically like pulses every so often, and then you read whatever is on the data. If it's high or low electricity, is like a 1 or a 0. Whenever the pulse happens, you check the state of the data line, and that tells you if there's a 1 or a 0 or not. So how does I2C work? Well, the first thing you need to do is the server has to say, hey, I want to start transmitting information. And the way that it does that is it pulses the clock and it puts the data down. Some details I'm going to lie there, but basically like the clock is high and the data is low. And after it does that, it sort of writes onto the data line, hey, this is the address of the thing that I want to do, and that's like 7 bits of information. And then 1 bit that says, is this a read or a write? Like, am I asking you to send me info, or am I sending info to you? And then the clients kind of listen on this data, and they go, oh, that's my address. Like, I'm the one that's supposed to listen to that. And then they kind of get control over the data line, and the other clients are required to be quiet while the rest of the adults in the room are talking or whatever. And so once the server says, hey, I'm trying to talk to client A, and I want to read information, the client gets to respond. I chose the second one in this example, but it replies with sort of this like acknowledgement of like, hey, I am in fact ready to receive the information that you want. And it does that by sending some bits along the line. And then since we described this as a read from a temperature sensor, the client then sends the data back over the data line, basically in the opposite direction from whenever the server sent it out. And those are in 8-byte chunks, basically, where it does those. And it does it until it's done transferring the data. And then it says stop. Stop is complicated and weird, and I don't have time to get into it, but it involves rising edges of clocks and stuff. It doesn't really matter for this purpose. But the point is just like, hey, I'd like to talk to you. Yes, I'm ready. OK, here's my data. Cool, I'm done now. Like, that's not that hard to understand conceptually. But like, that's how this stuff works. If you want to talk to many temperature sensors and clocks and stuff, like this is all you need to know. And there will be libraries that are written so you don't have to implement this on the low level. But even if we're talking about like hardware diagrams and stuff, like it's not something that is impossible for you to understand. It's actually kind of simple. And the simplicity is the reason why it's kind of a pain in the butt too, because like there's things that can go wrong and like whatever else. One of the things that sort of happens whenever you get into this area is you start to learn which APIs were designed by the hardware folks and which APIs were designed by the software folks. Because sometimes stuff is really awkward in software, and you're like, why would they ever give me this terrible API? And it turns out it's because implementing it in the hardware was easy, and they just don't care about you as a software developer. They expect you to paper over their bad APIs. So that does happen. So anyway, I just gave this summary, so I'm not going to read it again. But like fundamentally, this is like kind of very simple protocol. I've got a little over 10 minutes left, so I don't want to get super on all the things, but I have another story about a different situation that's much more recent. There's this concept in hardware called interrupts. And the funny thing is like in the software world, we talk about how synchronous computation is normal, and then asynchronous is this like weird thing we layer on top, right? hardware is like asynchronous by default, and we put synchronous APIs on top of those. So like ironically, like when you're writing your Node app or whatever, it's using asynchronous software stuff that's then turned into like the synchronous layer that then underneath is like also turned into an asynchronous layer sometimes. And there's better APIs you can use that get you directly into that asynchronous stuff. But just like the point is that like hardware is always interacting with the real world, and so there's not like step 1, step 2, step 3 like in a processor executing your code. It's like taking the ambient temperature every so often or whatever. Like the world is analog, not digital, and that also means that the things happen separately. So an example of using an interrupt in some code. This is, you use this interrupt annotation and with this one particular library, and you define a function that's the name of the interrupt. So this is the timer2 interrupt that happens on ARM. So sort of what happens is the processor kind of counts up for a while, and then when it hits a certain threshold, it fires off an interrupt. And you, by writing this code, you're just going to count how many times the interrupt fires by, there's a mutable variable, and you increment it, and it's like, fine. Like, you are installing this interrupt handler into this like vector table in your processor and a whole bunch of other fancy words. I was doing some intro to OS development stuff with my partner, Ashley, and I was teaching her about this. And I told her about interrupts, and I was like, a lot of people struggle with interrupts, or at least that's my experience. She had been working in JavaScript for a while, and she went, oh, this is like a callback. And I was like, yes. Like ironically, like some JavaScript programmers may be easier to understand some of these APIs than like traditional low-level systems people, because like they do a lot of asynchronous programming, and so it's a very natural style of designing this stuff. And so I just think it's kind of funny that like I never made that connection before, and I think it fits really well. So that's really cool. But this is like the way that you get a lot of stuff, like information that happens in the background. So like imagine you make a call over the network or something. Like what happens on like sort of the lower level situation is like your other code keeps executing, and then at some point in the background, the hardware goes, hey, I actually have the data for you, and then it calls back into you with an interrupt, and it wakes you up, and you do that kind of thing. So there's a lot of asynchronous stuff in embedded development, and that's also why I think Rust is a really fantastic language to do with it, because Rust has a lot of features related to asynchronicity and concurrency, and it can kind of help you navigate this kind of like, just like you can get spaghetti JavaScript with piles of callbacks, you can end up some really spaghetti interrupt handlers that like don't, that are impossible to debug and are really hard. I'm not gonna say that never happens in Rust, but I feel like it's just easier to not let it accidentally happen. You on purpose will make your own bad decisions you pay for. It's not like the language can prevent you from doing those kind of things. So anyway, I think one of the biggest differences, though, between the embedded stuff and the web world are these kind of what I'm going to describe as cultural differences between the two. And while I still think at the fundamental level, computers are computers, you know how to program computers, there are some ways in which embedded is different. And it's like, you kind of got to get used to it over time. So I'm going to talk about a couple of the ones that I tend to see or that I struggle the most with when getting into this. The first one is debuggers matter. I don't know about you. Maybe you use a debugger all the time. I'm not really a debugger person. I'm more of like a println, oh fuck kind of person, basically. Or like this, I should never get here, and then I see it pop up my screen, and I'm like, that's like my native debugging strategy. Turns out, like when you have a separate computer that like doesn't have a display, you can't really do printf debugging effectively, right? I already talked a little bit about semi-hosting being a problem, and so and also it's really useful when you're in that, like when I referenced crying in the debugger earlier, like sometimes you just need to examine the state of the system while it's running, and so there's a lot of tooling and a lot of like expertise that's been put into how do I debug these systems, and so you can hook up many kinds of debuggers. I personally use GDB in my day-to-day work to do this, but there's also, like we at Oxide wrote our own debugger, sort of, kind of, because reasons that are good, actually, but I don't have time to get into them. But the point is that like you kind of have to learn how to use the debugger as a skill, and it will be really helpful because it lets you pause the execution of the processor. Like when I use a debugger here, it shuts the thread down, but this is like shutting the whole system down, and then you get to examine the state and you get to figure out like where you made a mistake. And so that's kind of a big thing. Another really funny thing about debuggers, though, and the fact that you need kind of like hardware interfaces into debugging when you're doing this stuff, is like the complexity in not allowing normal people to use that debugger interface once you've shipped a product. Like I play a lot of video games. I found out people were like hacking their Xbox to do things in games. And I was like, I wonder what that's about. And I would go on eBay and like look up for this, and it's like, oh, we just turned the JTAG debugging interface back on, and you can plug your computer into the Xbox and then write to arbitrary memory because you're using the debugger to do that. And like that's how people cheat in video games. And I'm like, I now understand what those words mean. I didn't before, but like, oh, I've heard of JTAG. Like, cool, that makes sense. So anyway, debuggers are a big thing, and if you're not a debugger person, you kind of have to get a little bit more familiar with debuggers than not. I like big PDFs, and I cannot lie. I hesitate to say that the embedded world's documentation culture is good, but it does exist. Like your problem in web development is that you're going to get like either no documentation or some function signatures, and you kind of got to figure it out. The way that it works in embedded is they're like, here is a literally 300-page PDF with all those numbers I put earlier and what they mean, and charts and diagrams and these features, and this is how you turn this on and off, and that. So I'm like a documentation person. I like writing documentation. I like reading it. So that's kind of cool to me. But it's also true that documentation can have bugs. And so sometimes, like sort of in a similar way to the Rust compiler message thing I talked about earlier, where it's really good and it leads you down the path 90% of the time. So the 1% when it fails is very frustrating. Wait till you find out there's a hardware bug in the 300-page PDF, and you thought you found the one section that explains why it works, but it turns out that one line is wrong and that number is off, and like you're doing everything right according to documentation, but that's like actually a problem. So that's why the debuggers matter. But also, like, it's kind of nice because it's not like, how do I Google for the blog post where someone explained this? It's like, no. The whole documentation is in this giant PDF. And obviously people do write some blog posts, but like they don't cover everything, and you're kind of expected to learn how to look at, they call them data sheets, not big PDFs. I don't know why. Anyway, yeah, so that's a thing. TDD, as I mentioned earlier in the talk, I kind of like test-driven development, or at least in dynamic programming languages. Static stuff is a little more complicated. There's not really a culture of test-driven development in embedded software. It's not really a thing exactly. Now, in Rust, you can sort of kind of get that way, and there's actually some really interesting, like I said earlier, I like printf debugging. There's some tooling in Rust that exists that like saves all your printf messages on your computer and then replaces them with numbers, and then like uses the debug interface to like send the message back. And so you can sort of get a TDD workflow in Rust, kind of, but it's working uphill. And in a similar way, CI, like what, you're going to hook 1,000 Raspberry Pis up to GitHub Actions? Like that's, I mean, you can, someone probably has, but like it's not, there's a lot more like, it worked on my little tiny machine kind of like situations going on, and so that's like a big cultural shift. Okay, so I got 2 minutes left, which is great because I basically have a link to where I got all this information from, so you can sort of like, how do you go beyond this 2 versions of Hello World that I've shown you? Obviously, like I can't teach you everything about embedded programming, but I can point you in the direction of how to start off your journey. So the very first thing is this thing called the Embedded Rust book. This is put out by the Rust project themselves. It's a little janky. The people don't really work on it anymore, but it is how I learned this stuff. And it does a good job of walking you through a very basic project using a 32-bit ARM chip that is somehow still pretty available, even though for the last couple years it's been a little sketchy sometimes to buy certain hardware, but they chose a really good chip, and so it's there. There also is a thing that's pretty new. This is where I got my Hello World examples from, called Comprehensive Rust. This is actually a training material that Google posted that they use to train people on doing Rust, and it has an embedded section that I think is really great. It's a little hard to use without, it's intended for a teacher to be presenting it to you, so it's a little hard to read it yourself, but I really like it, and I think it's cool, so I wanted to give it a shout out. And then if you're trying to learn Rust generally, I'm very biased in that the Rust programming language is a book I wrote to teach you that, so I think it's good, but there's also a wealth of other Rust books, and you can Google Rust book and find them. And the last thing I wanted to point out is where I buy hardware from. So there's these 2 websites called DigiKey and Mouser, and they're kind of Coke and Pepsi of the embedded world, and sometimes the one place is out and the other place isn't, all those kind of things. But I have found that the key, and why I want to mention these things, is that again, with like the weird way that these companies are about their stuff, if I need to get a copy of that big PDF, it's actually easier to like go to, these are kind of like Amazon for embedded devices. You type in your chip. I don't intend on buying it from you. I have it there, but they'll just link the giant PDF right there, and it's like so much easier than trying to find it on the manufacturer's websites. So I would recommend that, like, even if you don't buy these things from those places, they're like documentation resources basically, and so you should be aware that they exist. So anyway, that is all I have for you today. Thank you so much, and I hope you enjoy low-level programming if you decide to get into it.